Welcome to this online session on Power Electronic Control Drives by Professor Tanuja Mbati from Electrical Engineering Department, Kewag Institute of Engineering Education and Research. Today we will be studying about induction motor drives. Now, in this topic, we will be studying induction motor speed control using stator voltage control and V bias control, and then comparison of these two motors. Now we are aware that when we look at the characteristic where speed versus torque is drawn for the induction motor, we can see the characteristic to be like this. In this we can see there are various torques which are plotted in the form of a characteristic versus speed. On x-axis we have 0 speed to synchronous speed, and various torques are developed. We call it static torque, we can call it pull-out or breakdown torque, we also call it maximum torque. Then we have this as operating region, where this torque is called as rated torque, or we call it full load torque. Whereas there are two regions which are seen. One is stable region of operation, which characteristic is linear, whereas from the maximum torque point on this side, this is a non-linear region of the characteristic, where more torque from this cannot be demanded and the motor enters into non-linear region. We are aware of this. When we consider induction motor is considered to be a constant speed motor, and we have two speed control methods which are widely used as stator voltage control method and V bias control method. We will see the details of this. Normally, the rated speed is very close to synchronous speed, and we know at full load torque, we consider the slip corresponding to rated speed is about 3%. The range in which the motor speed can be varied by maintaining the stable operation of motor is from this rated speed to the speed corresponding to maximum torque condition, where the slip is Sm. We say it is maximum slip at which the motor can still maintain the stability in the linear region. Any slip value which is from this slip towards slip equal to 1, which is starting point, all these slips, the induction motor enters into non-linear region, which is unstable region for the motor. So when we talk of speed control, we are actually talking of speed control of the motor in the linear region where it will be operating stably. Considering the stator voltage control method, we are aware of few facts, like the torque developed at all operating conditions is proportional to the square of supply voltage. Secondly, the slip at maximum torque is independent of supply voltage. These two are the facts which we are already aware of. Now this means that when we try to control stator voltage, the first statement indicates that torque will be proportionately varying if we try to reduce the stator voltage, and so torque will be affected mainly. Whereas the slip at maximum torque, which we said Sm, which decides the range of speed control, is independent of supply voltage. So these two are very important facts which we must remember. Now when we vary the voltage, the rule is we can continue reducing the stator voltage when torque required by the load is developed. So it is permissible how much we can reduce the stator voltage can be decided by what is the desired torque by the load, and so accordingly the speed control range is available. The stator voltage control method is suitable mainly for applications where the load torque also reduces with speed, which is typically in case of fan load, which we say fan or blower loads. The speed control only below the normal rated speed is available from stator voltage control, because the operation of voltages higher than the rated voltage is not permissible. We are aware that if we try increasing the voltage more than the rated value, it will put stress on the insulation which is provided, and so at any operating condition we cannot operate it at any voltage more than the rated voltage. So only range available for controlling the stator voltage is below rated voltage range. Now if we look at the stator voltage control, we can look at the voltage sweep torque characteristic of the induction motor at variable voltages. If we consider V1 to be the normal stator voltage, the rated voltage, and V1, we keep on reducing this. If we look at the characteristic of the induction motor, we understand that the synchronous speed remains same because we are keeping the frequency constant and we are reducing only the magnitude of stator voltage. So as we said, all the torques, starting torque, full out torque, full load torque, all these values will be reduced proportionately in square proportionality of the reduction in voltage. Okay, so this V2 reduced voltage characteristic is indicated, and if we continue reducing the voltage further, third characteristic of the same nature can be drawn. Now roughly if we say the point at which maximum torque occurs, which is indicated here, remains same. So the slip is independent of input supply voltage. What we said, SM is independent. So we can assume as if this point remains constant, which is SM point, and proportionally the characteristic keeps on showing reduced torques. When we look at the operating point, which is stable operating point for a fan load, this is the characteristic of the torques which are required by this fan load. We know that when motoring torque and load torque are same, the motor load combination can operate at a stable operating point. So initially when input voltage is the rated voltage, this is the operating point indicating N1 speed. When we reduce it to V2, the fan load requirement also reduces because this is also a variable load requirement of the fan. When the voltage reduces, the developed torque by the motor also reduces, but at the same time, the fan load requirement also is seen reduced. In such cases, the new stable operating point can be achieved, which is N2. So usually voltage is reduced with expectation of reduction of speed, which is achieved. For further reduction of speed, if we try reducing V3, then the new operating point, which is a stable operating point, can be obtained. But we can also easily visualize that if we try taking this voltage reduction further, roughly we can get a characteristic of this thing. And gradually we can realize that if we continue reducing this voltage further, there may be a point at which the load torque requirement is not met by the motoring torque. At such condition, now in this case this would be the next operating point, and for the last characteristic which I have drawn, it is indicating that this motoring torque cannot take the generate the torque which is required by the fan load, and so it fails. So up to this point we can have speed reduction. Usually, unless you have a fan load connected, which torque requirement also reduces with reduction of speed, this kind of voltage control is only suitable for such loads which are fan load. Imagine if this would have been a constant torque requirement, okay, if it would be a constant torque requirement, and we have some load which is suppose remaining constant like this. Okay. Suppose this would be the load characteristic. The first condition speed is here, second condition speed is here. In the third condition itself, it becomes a challenge that whether the motor will be able to generate this much torque, because it has almost reached the maximum load, maximum torque condition. So in such cases, the stator voltage control cannot be used, and it shows a limitation that it can be used only for very narrow range of speed control. Secondly, when we look at the efficiency expression, we realize that efficiency is given by the mechanical power divided by the generated power, PG, or air gap power, and this efficiency can be written as 1 minus S. Now, if we start looking at these reduced speed conditions, as the speed reduces, slip value keeps on increasing. In such case, difference of 1 minus S will keep on reducing, and it has direct impact on the efficiency. So it offers very poor efficiencies at very lower speeds. So these type of speed control is suitable only for fan and pump type of drives, where load torque also varies in square proportion to the speed. Okay. So this is a very simple way of controlling speed of induction motor, but it has these limitations. So it is applicable only for typical type of loads. Secondly, it can be used for very narrow range of speed control. This must be known. Now, to achieve this stator voltage control using solid state devices, these are various schemes which we have already studied in power electronics. We are aware that for single phase induction motors, variable AC supply can be generated by using thyristor voltage controller. We call it simple AC regulators. For low power applications, we can also use triac controller, where same type of variable AC can be generated, where only magnitude of AC voltage will be varied, and this is called as variable voltage constant frequency variation, because input supply frequency will remain same, only magnitude, so it can be used as stator voltage control. For three-phase induction motors, three-phase regulators can be used, and so using static controllers we can achieve stator voltage control, as which is discussed earlier. Now when we are talking of the other control, which is a V by F control, which is considered as a better speed control for induction motor, the limitations of stator voltage control can be overcome by V by F control. Now if we look at this characteristic, this describes two operating ranges which is showing torque versus speed characteristic. Now if we see carefully, from 0 speed to rated speed condition, we can see that this is a speed below rated speed condition region, in which torque can be generated to maximum value, and this is considered as a constant torque range of operation. Whereas when we try to operate it above rated speed condition, we cannot increase the torque, but the torque needs to be sacrificed or reduced proportionately, where power will be maintained constant. And so if we start looking at the expression, which is a well-known expression, we understand that this relation can be used by writing equation P equal to torque into speed, omega into torque. Now if we look at this, for below rated speed condition, omega will be varied from 0 to rated value and torque will be can be maintained constant at maximum value, where proportionate power will be derived or it will be linearly changing with reference to the speed at which we are operating, because torque is constant. So it becomes P directly proportional to omega. Whereas when we enter in above rated speed region, now we cannot extract more power from this combination, and so it reaches the maximum power condition. This power is now maintained constant. So omega into T equal to constant becomes the relation. In such cases, relation between omega and torque becomes inverse proportional. And so when we try to increase speed above rated speed condition, we need to sacrifice the torque. And so this curve, which is indicating the torque, which keeps on reducing when we try to increase speed above rated speed condition. So clearly these are two operating modes for any speed control methods. It can be constant torque region or it could be constant power region, where constant torque region indicates that we are operating below rated speed condition. For above rated speed operations, we have to enter the constant power region. Okay. Once we understand this, now we can try understanding the V by F control method. This is the expression which is well known to us. Input supply voltage can be written as a constant 4.44 into K into frequency into number of turns and flux. Out of this expression, we are aware that all these terms remain constant except for frequency and flux. So when we rearrange the terms, we can write the expression as flux equal to V divided by 4.44 Kf and T. T are number of turns, K is a constant and 4.44 also is a constant. So this can be converted into K into V divided by F. Now what this expression tells us, that if we maintain V by F ratio constant, we can also maintain the flux all constant, and since torque is proportional to flux, the torque developed by the machine does not get affected the way it gets affected in this case. So V by F control of the induction machine is a method which ensures that output voltage is proportionate. When we vary output voltage proportional with the frequency, it can maintain flux constant. There are advantages of maintaining flux constant, mainly because the torque which is developed by a motor is directly related to flux. Considering this relation, if we look at V by F control, it is nearly having the characteristic of this type. Now what are we doing? If we keep on increasing frequency up to rated frequency value and we keep on increasing the voltage proportionately up to rated voltage, then we can operate this in a linear fashion, where in the linear region the voltage to frequency ratio will be maintained constant, because this is a straight line relation. The dotted line indicates that the straight line can emerge from 0 up to rated condition. Whereas after reaching the rated frequency and rated voltage, at this point, we cannot increase it further above the rated frequency. There are reasons for this. Because proportionately we will not be able to increase the rated voltage above the specification or rated voltage, So we need to maintain the rated voltage constant even when we try to increase the frequency. So again, in this case, there are two clear-cut regions. One first region is below rated frequency operation, other is above rated frequency operation. Below rated frequency operation, proportionately we can increase the input voltage from 0 to rated voltage condition, and we will be able to maintain linear relation between voltage and frequency by keeping the ratio constant. Now when we operate from 0 to rated frequency, the induction motor speed will increase proportionately up to rated speed starting from near 0 value. Okay. So entire speed control range appears to be available, where proportionately voltage can be increased, frequency can be increased, maintaining V by F ratio constant, and we can operate in this region at practically at any operating speed. Whereas when we try to increase speed of the motor above rated speed condition by increasing the frequency, we need to maintain the voltage constant. So we cannot maintain V by F ratio constant in this region. So V is constant divided by increasing frequency. The ratio keeps on reducing, which indicates flux weakening region. Okay, in this region, so we cannot generate the same torque which we can generate in this range. This is again a limitation of V by F control. Now what is this curve indicating? This is more practical way of operating the V by F control. Though theoretically we said that we can operate from near zero speeds, practically while operating we cannot start with zero voltage. No motor can be started with zero voltage and zero frequency. So for very low frequency values, we need to, even at zero frequency condition, we need to give some initial voltage which is called as a voltage boost. Now this voltage boost is necessary to accommodate for some of the stator resistance drops which are otherwise neglected. So to overcome the stator resistance drop, this much voltage boost is required. So initially V rated needs to be boosted little bit, and the frequency can be started from near zero value. Practically, Fc is a cutoff frequency at which if we adjust Fc equal to this and the voltage is boosted, then we can ensure linear operation of this motor from this point to this point. So a small boost voltage in proportionality to maintain the V by F ratio constant from this region to this region. Below that, frequency would be very small, but boost voltage is required. So proportionately, we can gradually increase the frequency. Before that, that ratio would be higher. So initial boost is required to start the motor, and then we can operate it in any desired speed by maintaining V by F ratio constant. This is how this V by F control will operate. Okay, so these are specific things given. For operation below rated speed, voltage and frequency can be varied from low to rated value here. For above rated speed operation, this is a field or flux weakening mode where the voltage is maintained at rated value and frequency can be varied from rated to higher frequency values. But torque needs to be sacrificed. This type of V by F control is called as scalar control, and it can have applications in HVAC, which is heating, ventilation and air conditioning, fan or blower type of loads, where typically constant speed operations are required. But there are AC drives. Typically when we say, we have a combination of input rectifier which converts AC supply into DC, and then the inverter stage is available for generating any kind of voltage or control voltage requirements, voltage and frequency for the induction motor. So with these kind of arrangements, Various inverter control strategies are used and accordingly they are named. So typically used strategies are square wave inverter control, where we have studied that 180 degrees or 120 degrees mode of conduction is achieved for operation of these control elements. And then the motor receives voltage which will be uh, alternating voltage, but it will have a rectangular or square waveform. Whereas the other control strategy, which is more popular, is called as PWM inverter, where pulse width modulation techniques are used, like sinusoidal pulse width modulation, where number of times the switches are turned on and off. But the advantage is we can control the frequency as well as magnitude of the voltage by using any of these control strategies. So, controlling the induction motor for stator voltage control as well as V/F control is possible, and the drives which are utilizing such strategies are called as AC drives. They are very popular. Typically, the AC drives look like this. This is a configuration which can be used in general. Now, let us quickly check if we have understood. The stator voltage control for the speed control of induction motor is suitable for, there are four options given: fan and pump drive, drive of a crane, running as the generator, and constant load drive. Now, what is the correct option? The fan and pump drive is the correct option. Okay, so this is a right way of choosing the answer. Whereas V/F is maintained constant in the following case of speed control of induction motor. There are four options available: below base speed with voltage control, below the base speed with frequency control, above base speed with frequency control, and none of these. Now V/F is maintained constant. What is the correct option? Below base speed with voltage control, because then V/F ratio is maintained constant. If we try to operate above base speed, then the V/F ratio is not maintained constant. It will be reduced because V is constant and F is increased. So we can choose below the base speed with frequency control. This can be taken as the correct answer. Okay, so with this we can compare stator voltage control with V/F control. V/F control has a larger, wider speed control range, because practically we can control speed of the motor from near zero to above rated speed. Any of the operating speeds can be achieved by V/F control. Since up to rated speed the flux is maintained constant, we can maintain the torque constant and it can be operated in constant torque mode. But above rated speed condition, the torque needs to be sacrificed for constant power operation, and so that range is controlled by the torque requirement of the load. V/F ratio control method is more popular for wider speed control range applications, whereas stator voltage control is simpler but it offers narrow speed control range. It suffers from lower frequencies when it is operating at lower speeds. Okay, so with this, we will conclude this lecture. I hope you have understood two speed control methods of induction motor. Thank you.